Evet, ekranımı görebiliyor musunuz acaba?
Henüz paylaşım olmadı sanıyorum hocam.
Şu an share screen diyorum. Save.
Şu
Sizin
an
kabul et.
denerseniz sanırım paylaşılacak.
Am, Şu an nasıl? Hala paylaşılmıyor herhalde.
Bir kez daha deneyelim mi hocam?
Tamam. Share screen kısmından paylaşıyorum. Doğru mudur?
Evet hocam doğru.
Evet. Tamam. Şimdi sanıyorum açılacak. Şimdi.
Evet hocam görüyoruz sunumunuzu. Buyurun.
Tamam. Ee, Ben sunumumu İngilizce hazırladım. İngilizce sunmakta daha rahat geldiği için İngilizce sunum yapacağım. Siz Türkçe açılış yaptığınız için Türkçe cevap verdim. Herkese merhabalar. Hello everyone. Today I'm going to present my one of project titled Assessing Shallow Geothermal Energy Potential of University Campus in Balikesir, Turkey using Thermal Response Test. Today I'm going to cover introduction. I'll give you some background about shallow geothermal energy system, what this system is, and what type of shallow geothermal systems are available. And I'm going to present my studies objectives, study area, and geology. And I will mention about the method, thermal response testing. And finally, I will cover results and conclusions. And shallow geothermal systems usually use ground as a heat source and sink. And geothermal energy system rely on actually constant subsurface temperature because the temperature underground generally and mostly less than the air temperature in winter, in summer, and vice versa in winter. So the constant ground temperature usually reach at depth below the 10-meter depth, and we also take advantage of the natural geothermal gradient, which is 0.3 Celsius degree per meter, and the temperature is increasing when we go deeper. And this can provide us a stable temperature environment. And why is shallow geothermal energy system? Because this system uses ground as a free heat source and sink. So when we use 1 unit of electricity to run the heat pump, we can get 3 units from the ground. And this make this system high energy efficiency. And also this system use less electricity energy, and which cause less environmental emissions, CO2. And these systems' performance are defined by coefficient of performance, which is ratio of energy out to energy in. And the shallow geothermal energy systems basically implemented in two ways. One is ground source heat pump system. This system use the energy sources, use ground or underground water or surface water as the energy sources. So usually the conventional heat pump system use the air, but air varies the temperatures mostly, and this variation make the system less efficiency. When we use the ground, which has a constant temperature environment, you can get more efficient energy. And usually, if you have enough space, we can use the horizontal loop, but if you don't have any space, you can use vertical. So this is the picture shows the type of borehole that we use in this system. As a background, ground source heat pump system works not complicated. It has 3 units. One is the ground part, where the ground heat exchanger couple with the ground, and the heat pump part and the distribution system. And usually in the systems, we can, the desired temperature is 3 to 6 Celsius degree. This makes the systems efficient. So we will use leaving fluid temperature or T in, or entering fluid temperature as a T out. This is the representative temperatures we will use in the calculations later. The second shallow geothermal systems are underground thermal heat storage systems. In this system, thermal energy is stored in the ground for heating and cooling purpose. Actually, ground source heat pump systems are used for heating and cooling purpose too. But this system is store the heat to use the energy later. For example, it stored the heat during the summer and it used this heat during the winter. So this system are used three ways. One is heat energy stored in the aquifers. If the environmental geology has this type of aquifer, or and you can use this way. And also it can be used using the boreholes, which is really similar to ground source heat pump system. And the other one is the heat energy can be stored in the cavities and peat. This is also really common in Swedish and European countries. So based on this background, my objectives, most of the energy consumption is due to building or residential heating and cooling needs. And the reducing energy consumption in buildings is possible through the use of renewable energy sources in grid and the use of the energy efficiency. So introducing this type of energy system to university campus in Balikesir, because Balikesir is really high efficient, high energy potential area, especially wind and biomass, but the geothermal, also deep geothermal energy. But shallow geothermal energy is not used commonly compared to European countries, because the application process, the testing process is not well known. And I like to introduce the system to Balikesir. And to do this, I start with the state-of-the-art thermal response testing, because the ground thermal conductivity is the key parameter to design shallow geothermal energy system. This is the key parameter, and we need to find this reliable thermal conductivity values. And the best way is to run thermal response test. And based on this test results, we can evaluate the potential area that shallow thermal energy systems can be installed in Balikesir campus or other areas. And study area is, as I said, is located in the Balikesir Challenge campus. And this is stayed in the southern, northern west of the Turkey. It has coastline from Marmara Sea and the Aegean Sea. And the air temperature usually 0 to 32 Celsius degree. And it has a Mediterranean climate. And the geology, you can see these pictures. This is from the outcrop of the geology at the site. And based on the borehole logging and this site study, you can see the sedimentary rocks mostly available. And it can consist of limestone, clay stone, something like that. And at the field study, to run the thermal response test, we need to have a single borehole, and we did drilling and we did piping. After drilling, we need to equip the borehole with piping, and this is the U pipe that we will use for testing, and this is the grout material. And the thermal response testing, I will explain those parts in this section. Actually, thermal response test, it's use constant heat through the circulating fluid. So there is a mobility equipment here, and you can have a single borehole, and then the U pipe is brewed in this borehole, and then you can circulate the water. And this is a closed system. And under the constant heat rate, you can measure the temperature in to the well and out to the from the well. And based on those two parameters, temperature parameters, you can estimate the ground thermal properties. And we monitor, after applying the heat rate, we can monitor, as I said, T in and T out, and we will continue the test until the steady state condition is reached. This usually takes 72 hours. And after we get this temperature values, we plot the temperature versus time and to calculate the ground thermal conductivity and resistivity. This is how our equipment looks like. And here is the thermal response test mobility. We got this from Istanbul Technical University. And this is the inside this equipment. We have a ductwork here, and this is the water tank, and the right at the top is the automation system. And we monitor our results on the computer laptop. So here is the automation system, how automation system looks like. We set the heat rate, and then we measure the temperatures here. And this is our preliminary results. You can see we set the flow rates, 11 liter per minute, and these are the temperatures. T inlet, it's coming, the water coming from the well, and T outlets, it's coming from the equipment actually. So and we monitor these two temperatures until steady state condition reached, and the figures at the right showing the air temperature change. And this is why we have some distribution here because of the air temperature, the sudden drop air temperature. And the T inlet refers to water leaving the well, and T outlet refers to water entering the well. And the test is run under the constant heat rate. We also monitor the heat rate through the testing to see how our to see how much we succeed the constant heat rate in this machine. So the average heat rate usually used 3,000 watt, and our Q seems a little bit more than this, but it's okay. And to run some analytical modeling, we need to estimate the parameters. And our ground temperature properties are from the literature based on our local geology. And we have a density and specific heat capacity and thermal conductivity and the thermal diffusivity and the borehole, the piping radius and the temperature at the underground temperature. And the borehole properties, you can see the physical properties and the thermal properties here. Borehole length, we intended to drill 75 meter, but we stuck at the 56 meter because of the geology. It has lots of clay minerals, and it stuck make the drilling difficult. And we did this 56 meter. And borehole diameter 21.6 centimeters, and the U-pipe shank spacing, that means the pipes, the space between the two pipes entering and out pipe, and you can measure this, it's a 40 millimeter. And U-pipe outer diameter is the typical pipe. And these are HDPE pipe, Rihau pipe. I got this supply from Rihau because this is the one company that can provide this type of U-pipe. And this is also a thing I would like to give some comment. Getting the supplies for this type of applications are really difficult in Turkey. And so we need to get some this type of properties in our country, local country. So we, unfortunately, we depend on the abroad companies. And the lambda pipe, this is the point pipes thermal conductivity and the grout thermal conductivity. These are all literature from literature. And And we, how we calculate the thermal conductivity calculation. So there is two ways. One is the Kelvin's line source methods, and the second one is the cylindrical source methods. Usually for thermal response test, we use Kelvin's line source methods, and based on our values, Q values, heat rate per meter, and divided by the multiply by pi, multiply by 2.9. We got 2.59 from the data fitting that we get from the parameter estimations. So we plot the mean temperatures, and now we fit our fluid temperatures, and then we got this fluid temperatures constant 2.9. And based on this Kelvin's line source methods, we got thermal conductivity 1.73 watts per meter Kelvin. And we also use the cylindrical source methods, and this is the approximate equation for fluid temperature. First of all, we estimate the fluid temperatures, and then we compare these temperatures with our experimental results.
Ayşe Hocam, son 2 dakikanızı hatırlatmış olayım.
Okay. Okay, then and we compared our experimental results with the analytical circulating cylindrical source methods. So you can see here that we got this nice fitting curve, and we got 2 watts per meter Kelvin. So finally, a state-of-the-art thermal response test was successfully conducted in this campus, Balikesir University, and thermal conductivity values obtained as 1.73, and 2 analytical methods were conducted, and line source and cylindrical source methods. And cylindrical source method provides a better match with experimental data, and further study is still needed for assessing the shallow geothermal energy potential in terms of ground source heat pump system application in this university. Thank you very much, and I'd like to thank you, the Balikesir University Scientific Research Project, providing the budget, and Dr. Murat Aydın for his valuable guidance and help. Thank you.